As was mentioned, my name is Andrzej Lamecki and I'm from Warsaw University of Technology. And today I will talk about our paper titled Hierarchical Data Structures in Rendering Scenes Containing a Massive Number of Light Sources. So first I will define our problem. We want to render a scene containing many, for example, several thousands light sources. All light sources are considered to be point lights, which means that they have a defined position in a scene and a limited range. An example of such scene can be seen in the picture on the right side. There we have a scene with 1 million point lights. All lights on a scene are considered to be dynamic, which means that their position can change between frames, so we cannot bake the lighting into the scene. The main problem is how to calculate lighting for each object on a scene, because each object can be affected by many lights, and each light can affect multiple objects at the same time. The most popular approach to this problem is dividing the rendered image into two-dimensional or three-dimensional cells. An example of such division can be seen in the picture on the right. There we have a rendered image divided into 32 tiles vertically and 32 tiles horizontally. Then after this division, we assign to each cell a list of lights that possibly affect any geometry contained in that cell. Then during the shading process, we read the information from the list corresponding to the cell the shaded pixel is in and check if the light really affects the color of a pixel. Examples of algorithms using such methods are tiled shading, clustered shading, and the newest one, hybrid lighting. The problem of rendering scenes with many lights comes with many challenges. The main one is non-continuous geometry in cells. In the picture on the right side, we can see a close-up on one of the tiles from the previous image, the one highlighted in red. In this tile, we can see 5 objects, each in a different distance from the camera. Each one is highlighted in a different color. The non-continuity of geometry in a cell is a problem because if objects are in a different distance from the camera, they are unlikely to be affected by the same set of lights. So if we have a set of lights assigned to a cell, then we will have to process a lot more lights than necessary. The obvious solution is subdividing the cell into smaller ones. However, with the more we have cells, the more time we have to spend assigning lights to these cells. The other two related problems are non-uniform lights position distribution and lights with highly variable range, because the algorithms that I mentioned all assume uniform space distribution. Now I would like to describe our proposed algorithm, which uses hierarchical space division. The algorithm is based on the hybrid lighting algorithm, which means that we divide the rendered scene into three-dimensional cells, and we use billboards to efficiently assign lights to cells alongside with the graphics pipeline. The cells, however, are grouped into an octree, and we allow to assign lights not only to leaves of the octree, which represent singular cells, but also to internal nodes of the octree, which represent group of cells. This hierarchical approach helps us to handle lights with variable range and non-uniform space distribution. We use a sparse octree representation, which means that we only store the nodes that contain any geometry. For this, we need to determine which cells are present in each frame, for which we are using one of the 3 proposed methods. We then insert each node using an iterative algorithm. We have also adapted the octree to handle an arbitrary number of cells in each dimension by simply extending it to the nearest power of 2. In the picture on the right, we can see an example of such extension where we use a 4x4 quad tree to represent a 2x3 division. Once we have built our org tree, we have to assign lights to it. We assign, as I mentioned, lights not only to leaves, but also to the internal nodes representing groups of cells. We decided that we assign a light to the internal node if it could be assigned to each cell in group represented by that node. For this, we are using cells corners positions and compare them to the compare their distance to the position of the light with the light's range. In the picture on the right, we can see two situations. On the left side, we can see that the light represented by the yellow circle cannot be assigned to the group of 4x4 cells represented by the black grid, because the cell highlighted in yellow is not in range of the light, which we test using the distance of the blue points representing the cell's corners to the origin of the light. In the situation on the right picture, we would assign this light to a node representing this group of cells. During the shading process, we then read information from all lists on the path from the root to the leaf representing the cell the shaded pixel is in. We have tested our algorithm and compared it to other algorithms, clustered shading and hybrid lighting. We have used 4 different test scenes. The 3 of them, the Cornell box, Sponza, and Rungholt, are well-known scenes used for graphical benchmarking. And the 4th one, the bars scene, we have created specifically to test many discontinuities in geometry. The complexity of the scenes varied from about 30 triangles in case of the Cornell box scene to about 6.7 million triangles in the Rungholt scene. And the number of lights ranged from about 2,000 lights on the Cornell box scene to 1 million lights on the Rungholt scene. We have tested 3 different tile counts for dividing our image, here represented in the table by each column. We have tested each of them for all 4 test scenes, each represented by a row. The numbers in the table are average time for the test, for the moving camera, for the test average across all frames, and the percentage change from the first column. And we have noticed that the lower the tile count, the lower time we needed to render a frame in average. We have also tested a few different methods of dividing space in depth. We have tested 2 different cell counts in screen space and in view space. And we have noticed that there is not much difference between the same division method, namely if we divide it in view space into 128 cells or 256 cells, it's not much of a difference. However, it is much more important how we divide these cells, because division in view space resulted in overall lower average rendering times than dividing it in screen space. We have also tested an exponential space division method in depth, which meant that we divided the depth in view space into cells that are as close to a cube as possible. Here we can see a graph of rendering times for each frame for a Rungholt scene. The horizontal axis represents frame number, and the vertical axis represents rendering time for that frame for 3 different division methods in milliseconds. And the exponential division scheme resulted in overall comparable times with the view space division. However, the screen space division resulted in a lot higher times in most part of the test. In these parts where the times were comparable for all three division methods, the camera was close to the objects on the scene, and it resulted in not much of a difference in rendering times. We have also compared our three methods of determining a list of unique cells to build an octree. We have used an approach with bit masks, and also with sorting and removing all repeated keys of cells present in on a given frame. We have also extended this method to remove elements before sorting, so we have to spend less time on sorting the keys. The lowest times were achieved for all our test scenes for the approach with bit masks, and with the sorting-based methods, removing repeating elements before sorting the lists also proved to be beneficial. As I've mentioned, we have also compared our algorithm with two different algorithms, namely clustered shading and hybrid lighting. We have also tested two different tile sizes in pixels for each algorithm, here represented by the numbers in parentheses. In these graphs, we can see an average frame rendering time for different number of lights in a scene for two different test scenes. The vertical axis represents an average frame rendering time in milliseconds, and the horizontal axis represents a number of lights in a scene in thousands or millions, depending on a scene. Our algorithm achieved about twice as big rendering times on average for more lights on a scene than the other algorithms. But if there were fewer lights in a scene, the rendering times were comparable. Here we can see graphs with showing the average total number of lights or light list elements during the rendering process. We use this to approximate the memory requirements for rendering of the scene. And here our algorithm achieved much lower results than the other ones, especially in the sponsor scenes. No matter how big the tiles were and how many cells there were, it achieved lower average number of light list elements compared to the other ones. To sum up, our modification allowed for a reduction of light list elements by up to 65%, which resulted in reduced memory requirement. However, there are still some issues with multi-threading in current implementation, because the same operations are performed by multiple threads many times, which results in overall slower algorithm than the other ones. However, the rendering time is still comparable in some cases. And that would be all. Are there any questions?
Yes, thank you very much for the presentation. Do you have any question? I see hand raised from Mr. Konrad, probably Konierski. Please, I think you can unmute yourself, or
Yes.
Yeah.
Good morning. I have a question. How this method will work when we have like a semi-transparent object, or like a reflection of the surfaces?
We didn't really consider that, because that's a different, let's say, part of the rendering stage. None of the algorithms specifically mention that, because they are designed for lighting the scene of the opaque objects.
Okay.
So we didn't really consider that, but that and also probably a follow-up question would be how to handle shadows with so many lights. So yeah, that's also a thing for consideration.
Okay, thank you.
Okay, I don't see any more hands raised. I have a question with respect to the results. If you could once more show the diagrams, but the ones when your method got worse results. I think the next one.
Okay, maybe I didn't. Yeah, this one.
Yes. Okay. I think this were the slides where you mentioned that the method actually performed worse than other algorithms. And do you have explanation for such behavior? What's the reason for it?
Okay, maybe I explained it. These graphs show that our method is better in terms of a total number of light list elements because it requires less memory, and this slide shows that it requires more time. Okay, yeah, and this one is the most probable explanation, I would say, is, as I've mentioned, the problem with implementation, because we have based our implementation on billboards, which we discovered later that do not suit our approach exactly, and it would be probably beneficiary to change this part of implementation. But yeah, I believe that that's the main issue with and all the other results prove that this is the main reason it's that much slower than the other algorithms. Okay.
So probably that's also the answer to my next question. So what about future work?
Yeah.
So
that's probably we would have to rewrite the light assignment process to not use billboards and to maybe lean towards something more like the cluster shading algorithm, because there are differences in our implementation. Each light is processed sequentially by multiple threads, and it would probably be beneficial to process it the other way around if we're using a hierarchical approach.
Okay, thank you for the presentation. Very interesting work.